All right. Good morning, everybody. Thanks for coming here. I'm Misty Biswas, and I'm from SRF Consulting Group. Today, I'm going to talk about application of Freeway modeling outputs from Vissim to assist and help the decision-making process in complex Freeway projects. So let's get started. So I will start with an overview of my presentation. So I will go over the study area, the project purpose and need, the evaluation process that we came up with, our initial screening process, our alternative comparison screening process, and last I will go through the conclusion and the next steps for our project. So this is the project area. As you guys can see, it's in Midwest, Minnesota. So this is our study corridor. So we modeled the I-494 corridor starting from the Trunk Highway 62 all the way to the airport. And also kind of to see what the effect of this project on the cross freeway, we also modeled Highway 100, I-35W, and Highway 77. We also modeled the intersections alongside the corridor to see the impacts on those intersections and arterials as well. So in total, it was 60 miles of freeway and 37 intersections. So it's a huge model. So this is the study area. This is the freeways and the arterials I was talking about. And I'm not going to read this back to you. It's the same thing that I kind of show you in the last slide. So I'm moving on to the project need. I-494 is a major freeway in Minnesota. It connects the communities with the large employment and the shopping centers. So we have our Eden Prairie Golden Business Triangle right here. We have our Mall of America, the biggest mall in the US, and we also have our Minneapolis-St. Paul International Airport. So needless to say, it's a very important corridor, and the congestion in this corridor is pretty bad. So much so, few segments in the corridor actually stays congested in the peak hour, even in the weekends. So the purpose of these projects are three mainly. So we want to improve the safety and the mobility along the I-494, the travel time reliability for all highway users, and we also want to improve and maintain the transit mobility along the corridor. So here goes our evaluation process. So it's kind of a three-phase process. So in the first phase, we do our initial screening. So we come up with a bunch of alternatives and we kind of see them from high level, that how that impacts or how that looks like in terms of our evaluation criteria. So we have our mainline alternative screening that we do for 494. We reconfigure some of the access point along 494, and we also remodel or redesign the I-494 and 35W interchange. So in our phase one, our initial screening, we came up with a bunch of alternatives and we go through our screening process and we carry forward some of the alternatives in our phase two, what is alternative comparison screening. And in phase two, our microsimulation or Vissim model comes in. We compare all these alternatives against each other head to head, and we kind of come up with our identified or our recommended alternatives. And in the phase three, we are going to combine all these changes and we're going to see what kind of effect that does have in our congestion and also in our highway impacts and all these benefits. So here is our screening, initial screening focus area. So as I mentioned in the previous slide a little bit, we have three focus area. The first of all, we want to improve the 494 main line, right? That includes adding a lane in each direction. Second of all, we want to improve the access in this area. So this is from Lindell and 12th. So this area, we also kind of running our Vissim model, we're running our evaluation process to see how this area improves with different kind of access reconfiguration and also how the traffic impacts the arterial in that area. And last but not the least, we want to improve this interchange, which is a major interchange connecting two major freeway, the I-35W that goes north to south, and then the 494. So kind of the driving factors between kind of choosing these three focus areas. So these three focus areas actually focuses on different issues happening on that locations, and the impacts are different in these locations from one another. Another kind of benefit of having these three focus areas is the funding availability. So this is a Minnesota DOT and FHWA funded project. So if we kind of break it down in 3 stages, we can do construction in 3 stages, and we can also have the funding availability in 3 stages, and all of this can also work as a standalone project. So that's why we kind of break it down to 3 major areas when we look into the improvements. So here comes our initial screening process. So initial screening process for our 494 mainline alternative. So the first one is of course, our do nothing option, the no build option. So we keep it as is. The next one is our min pass option. So our managed lane options, which we call min pass lane in Minnesota. So we add a lane in each directions, and if you're 2+ users, you can use that lane for free. But if you're a single rider, you have to pay a fee to use that extra lane in peak hour. Then we have our general purpose option, which is also one additional lane each directions, but that lane is open to all traffic. We have our HOV options, so only the HOV vehicles will use the additional lane that we added. And lastly, we have our 2 barrier separated options. So we have 3 traveling lane and 1 barrier separated lane, and another is our true traveling lane and 2 barrier separated lane. So in this stage of our modeling, we use travel demand modeling to kind of see the right-of-way impact, the lane utilization, and kind of have a high-level overview on the cost. So we move forward with our 3 alternatives: our no build, our general purpose, and our min pass, which is our managed lane options. And we rule out our HOV lane options because when we did our travel forecast modeling, we do see the extra lane that we assigned to the HOV vehicle was not fully utilized. So that's why we rule out our HOV lane options. We also rule out 2 of our barrier separation options because of the high cost and the high right-of-way impacts. Also, in the travel demand modeling, we don't see much of a travel time benefit for these alternatives over the general purpose alternative. So at the end of our initial screening for our main line, we move forward with no build, general purpose, and the min pass or the managed lane options. So the next we have our access reconfiguration alternatives, right? So in the access reconfiguration alternatives, as I mentioned before, we look at from our Lindell Ave and our 2012 Ave. So as you can see in the existing, there are kind of closely spaced intersection that has full access in Lindell, full access in Nicollet, and partial access in Portland that works as a split diamond. So kind of the alternatives that we came up with is our no build, our Portland access, our Nicollet access, and our split diamond between Nicollet and Portland. And within our Portland alternative, we also have a bunch of alternatives that interchange design that we looked into. So now this is our existing configuration. So as I mentioned before, we have full access in Lindell, full access in Nicollet, and we have a split diamond between Portland and 12th in here. In our Portland alternative, we give full access to our Portland, and we took out access from our Nicollet and take out access from our 12th. So in our Nicollet alternative, we keep full access in Nicollet, and we took out access from Portland and 12th. In our split diamond alternative, we take out the partial access from Nicollet, and then we give partial access to Portland in the east direction. So in that case, the Nicollet and the Portland kind of works as a split diamond here. So we kind of go through the same process in our access configuration summary. So we see how the volume will look like when we take out access, how the vehicles will move to different intersections, and how will that perform. So we have an overall look in all of our access consolidation, and we move forward with our no build and our full access in Portland. So we rule out our full access in Nicollet options because the loops in Nicollet doesn't meet the minimum radius recommendation, and to meet that we'll have a high cost and also a high roadway impact. And when we looked into our split diamond option, it kind of ranks the lowest in our operation and safety aspect, and it also closes twice as many access compared to the highest performing alternatives. So at the end of our initial screening for access, we move with no build and full access in Portland. So as I mentioned before, in Portland alternatives, we have our tight diamond interchange, we have our diverging diamond, we have our roundabout, we have our Texas U-turn, and we have our single point urban interchange. So we are gonna move with all this to our Vissim model. And lastly, we have our initial screening for our interchange design in 494 and 35W. So here we come up with two alternatives. So as you can see here, we are building a flyover and a braided bridge in here. In both of the alternative A and 2, the difference between alternative A and B, alternative A and B is the 82nd Ave. So in alternative A, we have ramp access in the north of 82nd. At alternative B, it becomes a frontage road, so it ends in here, and we do not have an access going back to 35W in alternative B. So to evaluate our options, we move forward with both of these two alternatives for our next phase. So kind of I wanted to mention what we did before our initial screening. So we modeled our 60 mile of freeway and 37 intersection with Vissim 10, and we also calibrated, right? If you don't calibrate, it's like garbage in, garbage out. So we calibrated our 5-hour model with detector data, with field data in every 0.5 mile of the corridor, and we calibrated that against the volume and the speed. So we matched the volume and the speed to a considerable level in each 0.5 mile of our corridor in 494 and the cross freeways. So we modeled the 5-hour of AM and 5-hour of PM. But outside that, we also do a half-an-hour seeding period before the simulation starts just to get the congestion and starting, and just to get the traffic in the model. And we also do an hour of cooling period. So what I mean by that, we send a lower vehicle input in the last 1 hour in each 15-minute period, so that we can clear out the congestion and we don't have as much latent demand at the end of the model. So we want to have the end of the model kind of moving in a free flow. We didn't want to end the model and we still have a lot of congestion that we are not considering in our alternatives. So that's what we did. We built our model, we did our calibration, we submitted to Minnesota DOT and FHWA, so they reviewed it and they said it's okay, just let's move forward. So this was our existing model, and based on that, we do our 2040 forecast, and we build all of our 2040 models. So next step, we come to our alternative comparison screening criteria. And as you guys can understand, this is a huge project and we have a lot of criterias. I'm mentioning only the criterias that are related to traffic, and I also kind of highlighted the ones that we got from Vissim output. And I also kind of show you guys our scoring system, which is like not a typical 1, 2, 3. We kind of have a all black fill circle, that's our desirable. The 3/4 fill is our above average. The half is our average. 1/4 is our below average. And the kind of the empty one is we don't want that. So in our alternative comparison screening process, we did the Freeway level of service. So we collected our link results for all the links in 494. So what did we do with the link results? So once we get our link results, we know in each link the speed, the density, and the volume, right? So from the density, I only have 10 minutes, right? So from that density, we came up with the level of service for each link. So we kind of come up with, okay, so what is the level of service D or better in our no build condition? What is the level of service E or F in our no build, our min pass, and our GP condition? So as you guys can kind of see here, we have more kind of lane miles in our GP and min pass than our no build. You guys have any idea why is that? Because we have an extra lane, right? We added a lane in each direction in our JP and min pass, so we have extra lane miles, but the lane miles kind of added more in a level of service D or better, not in level of service E or F. So if you go to our next slide, I kind of show that in percentages to better compare it against one another. So if you can kind of see, we have 6% level of service F in no build, that goes down to 17 in our general purpose, and that goes down to 20 in our min pass lane. So kind of if you go back to the slide, we can see our GP can overall performs better than our no build and our min pass. So next is our kind of freight traffic. So we look at our freight traffic in the west of 35W and the east of 35W in our 494. So in this case, we use our travel time outputs from Vissim, and we compare it in both AM and PM, and we combine them together to see how our no build performs against our GP and our min pass condition. So as you can see here as well, the GP performs the best, and then goes the min pass, and both the min pass and GP kind of performs better than our no build. So now we came to our crash reduction. So what we did for our crash reductions is we did use our vehicle trajectory files, our individual vehicle information from Vissim, and we put that into safety software that FHWA builds, is SSAM, the Surrogate Safety Assessment Model. And we kind of came up with, so we calibrated that against our existing condition to kind of see how the crashes are against in our existing condition. And then from there, we kind of get a crash rate for our no build GP, and we kind of put a dollar amount in our increase of the cost, crash cost, in our min pass GP and no build condition. In the next step, we have our access consolidation model. So we have our intersection traffic operations. So in this case, we kind of figure out which are the intersection that performs level of service worse than level of service D. So we kind of see report the level of service for all our alternatives, our TDI, DDI, Texas, Roundabout, and SPUI, and we kind of see our Texas, SPUI, and TDI has a better level of service than our DDI and our Roundabout. So we use the Vissim node results for this analysis. And then we have our overall VHT data, or the system travel time data that we used. So we have, we kind of show here what are the changes in between our no build and our access changes. So our access change actually performs better than our no build. And we also kind of compare all our Portland build alternatives, our DDI, TDI, Texas, Roundabout, and SPUI. And in that comparison, our Texas and SPUI performs better than the others. And we use kind of the travel time from Vissim network results. Then we have our transit performance. So we have 27 transit routes in our corridor. We can just see how the transit route travel time performs in all our alternatives. And we kind of score them at the same way, and we see that our Texas and SPUI also performs better than our other alternatives. So lastly, we have our alternative comparison for 35W, and this is where things get a little interesting. So similarly, we use the Vissim link results, and we combine, we use the speed density results for each link, and we calculated the level of service for the link, and we know the link length. So we combine the lane mile for each link, and then we have our no build condition, our two alternative condition for 35W alternatives. And if you kind of see here, our no build actually performs better than our alternative A and B. That's because when we improve 35W, we're opening a gate, but 494 is still congested. So this traffic cannot flow into 494, which causes additional congestion. So it kind of gives us important information about staging of the construction. So we have to make improvement in 494 main line before we do our access, or before we make improvements in 35W and 494 interchange. So this results kind of shows the similar thing. We use that Vissim network results here to calculate the VHT, and we kind of see it's not any better than our main line. So here comes kind of my conclusion that we came up with from my presentation and next step for our project. So kind of overall, in our alternative comparison, we see our general purpose and our min pass condition performs better than our no build, and our Texas U-turn kind of performs better than our other Portland alternative, and mainline improvements needs to happen before we make any changes in our 494 other access or 35W interchange alternative. So the next step for our project will be combining all these changes to see if we improve the 494 main line, if we change the access, and if we improve the 35W alternatives interchange design, how that impacts our travel time, how that impacts our transit, and how that impacts our crashes, and how that overall impacts the traffic in this area. Thank you. Do we have time for questions?
Any questions?
Yeah, go for it.
So I've got two questions here. Could you speak more to how did you did your calibration to speed, and the other one is what was your criteria for your level of service? You said it was based on density.
Yep.
So what was the thresholds for?
So it's the kind of. Thank you. So to the first question, so we so in Minnesota we have detector data every 0.5 miles. So that's why what we used for our calibration data. So we have every 0.5 mile we have our detector data, we have our volumes, and we have our speed data, right? And then from Vissim we used our data collection points. And then at the same location that we have detector in the field, we put our data collections point to compare the speed and volume in that location. And then we kind of compare our speed density curves.
But the initial speed that you set in your model, was it based on like the posted speed, 85th percentile?
So the initial speed in the model is based on our detector data. So the desired speed, are you asking about the desired speed?
Yeah, so you already had it set based on what data you had from the field.
Yes, but then we calibrated our lane behaviors so to create the congestion. Yep, where there is congestion in the freeway already. Yep.
And then the second one was your criteria for level of service based on density.
Yeah, so for the level of service, we actually got the, for each link in 494, we get our link results, right? So the link result kind of shows you your speed, your density, things like that. So the density, I think we used the density level of service. So density 45 or lower is a level of service D, and then we have like our E and our F for every kind of bucket.
And where was that coming from?
So that's coming from kind of few other work that we do with MnDOT, Minnesota DOT. They have their kind of set of density versus level of service, assigning the specific density to a level of service. So that's what we use it for.
I think MnDOT's based on, it's either like an HCM or NCHRP.
Yep.
For density.
Yep.
So those are out there if you look for them, and it's kind of similar thresholds.
Yeah, I think it's like 45 is the level of service D, and then it just kind of goes to different level. Any other questions? Yeah. Any of you want to go first?
Did you said you used trajectory data to feed in
It's the same, yeah.
Did you do the entire 60 miles corridor, or did you break it down?
So,
in my experience, SSAM is one thing to extract trajectory data for entire this 5-hour peaker model. It can take, I don't know how long of a time, and SSAM is not that unified. It can crash with that large amount of data.
Yes, it's a good question. So we did kind of different staging for different projects. So for the mainline project, we used the entire mainline model, and we load that into SSAM, and I keep working in other projects because it takes a while to upload the data. So it took a while for us to do that, but while extracting the data from SSAM, we actually kind of did some spreadsheet tool. So we kind of select the link that we want, so that we can separate the mean line from the, the conflicts in the intersections and so on and so forth. So it took a while, for sure. But it didn't crash.
Selected data in SSAM, not the entire trajectory.
We did put the entire trajectory because if you see in Vissim, there is no way you can crop it. Yeah, you cannot crop it, so you have to put the entire data. But when you're analyzing it from SSAM, and you can write it down in a CSV file, and you can, sort it then. Your question, please.
When you were talking about the cooling period that you had for your volumes, was that an hour after your 5-hour peak, or is that the last hour of your 5 hours?
Yeah, so let me go back to that slide. So, yeah, so when I was talking about the cooling period, that's after our peak hour. So what I mean by the cooling period, so, our model records the data from 5 a.m. to 10 a.m., and then after 10 a.m., I send a lower rate of volume input every 15 minutes for that an hour. So I think that's like 25% of the last hour. And then we just kind of use that cooling period to clear out any congestion. So all we wanted at the end of the model, we didn't want any congestion or anything to stay in the model. We wanted the model to go in free flow. And as you can see, we're using 2040 data, and it's already a very congested corridor. So we just needed that extra time.
Okay.
That answers all the questions, and I'll not take any more time then.
All right, well done, well done. Thank you.